Okay, so let's continue discussing polarity a little bit here. So we kind of went through the procedure or process to kind of develop what the polarity of the molecule is, but let's just go through some examples, and we're going to start all the way back at the molecular formula. We'll draw some Lewis structures, we'll identify the shape, right? And then we'll also apply what we've talked about in terms of polarity. So some of these molecules we've seen before, but I think it's important for some of them that we kind of specify what's going on. So let's start with water, right? So if you're given the formula H2O, right, you would either start with drawing the skeleton or identifying the number of valence electrons. Hopefully, skeletal-wise, you'd recognize oxygen should go in the middle, right? And that's not because of electronegativity. Right? Often we want to put the least electronegative element in the middle. It's because of hydrogen's inability to have more than 2 electrons. So hydrogens can't go in the middle because we don't want to make bonds, 2 bonds to a hydrogen that would connect it to both the other pieces here. So oxygen goes in the middle. Oxygen comes with 6 valence electrons. Each hydrogen comes with 1. The total would be 8 valence electrons. Right? We already used 4 by putting 2 bonds into our skeletal structure. The last 4 would have to go on the oxygen, right? Now, that's a good structure. 2 electrons on each hydrogen, 8 on the oxygen. Formal charges are also good. They're 0 for each one, right? So it's 1 minus 1 for the hydrogens, 6 minus 2 minus 4 for the oxygens. Again, you may want to go back to chapter 8's videos if you're not up to speed on your formal charges. That should be something you can evaluate just by looking at your structure, right? At least at the point you come into the test, you should be pretty good at doing that and not have to spend a lot of time, kind of grinding out what are the formal charges there. Now, from here, this is where we would start to apply our geometry evaluation. Looking at the central atom here, the oxygen, I would notice 4 sets of electrons. So I wouldn't think, oh, I drew that as a line, it's linear. I'd think, oh, 4 sets of electrons. That's actually a tetrahedral electron geometry. And I'm not going to make you guys draw the 3-dimensional structures. It is certainly something you will do if you continue on in probably any science. You'll need to develop some ability to visualize 3 dimensions. Certainly if you take more chemistry classes, if you go on to sophomore level organic chemistry, a lot of that's based on evaluating 3-dimensional structure. So it's not a bad idea to get used to doing that. Drawing it does help your mind develop the ability to picture it as well. But the molecule would really look more like this because it is angular, right, or bent. From here, we'd want to think about the polarity of the bonds. So we'd look up the electronegativity of oxygen and of hydrogen. Oxygen's more electronegative, so each of these bonds are pulled in toward the oxygen, right? The electrons are being pulled toward the oxygen. Because of the angle here, remember this is about a 109.5 degree angle, the dipoles, or the polarity of the bonds, is not going to cancel out. It's going to add together. And in this case, we end up with a partial negative side of our molecule there on the side where the oxygen is, and a partial positive side on the opposite side, and the electrons are being pulled away from the hydrogen, so the hydrogen side, and that makes this a polar molecule, right? So water is a polar molecule. Let's look at another example. Let's see, let's do H2CO. Let's throw a carbon in there to see what we get there. So in this case, right, if we think about formal charges, hydrogens are going to make 1 bond, tend to want to make 1 bond. Carbons are going to tend to make 4 bonds. Oxygens tend to make 2 bonds, right? That means carbon is the best one to put in the middle here. It's going to make the most bonds. It's also the lower of electronegativity between the carbon and the oxygen. Again, the hydrogen can't go in the middle. So a good start might be this skeletal structure, right? And from there, we'll need to think about the total number of electrons and where we want to put them. So carbon is 4, oxygen is 6, and then 2 hydrogens here, each bring 1. That's a total of 12 electrons. We already used 6 because we made 3 bonds here. Now we want to start on the outside of the molecule. Hydrogens don't need any more, but oxygen needs all of them to get to the octet. And once we get all the electrons in, then we can look for the octet rule in the rest of the molecule. Oxygen is fine, but carbon only has 6 electrons here from the 3 bonds that we've given it. So to fix that, I want to share from the oxygen and make a double bond here. So if I have a double bond there, I end up with this structure. Now, I actually drew this structure, and I have to purposely try not to do this when I'm doing a lecture, because I may have already given away the shape here, because I drew these with about 120-degree bond angles, because this is trigonal planar in terms of its shape. I try not to give that away when I'm drawing. I manage to remember with the water to draw it straight instead of the way it really is bent. But this is 3 sets of electrons. 1, 2, 3. 3 sets of electrons will go to the corners of the triangle. Trigonal planar electron geometry, all bonds here. So this is a trigonal planar shape, or trigonal planar molecular geometry as well. Now, if we do then want to determine polarity, right, carbon-oxygen has a difference that the electrons are going to be pulled toward the oxygen. Carbon and hydrogen are fairly close, 2.5 and 2.1, but there's a little bit of pull towards the carbons. So all these arrows are pulled in and up toward the oxygen, and that would make this molecule have a negative end where the oxygen is, and then on the opposite side would be the positive end. This is also a polar molecule. And this is an example. This is kind of what I talked about toward the end of the last video, right? The trigonal planar geometry is one that could be symmetric, right? Remember, if it's symmetric, even if the bonds are polar, they're going to cancel out, and the overall molecule is going to be nonpolar. But if you have that potentially symmetric shape, but different things are in those positions, then those polarities of the individual bonds may not cancel out, which is the case here. Okay. A trigonal planar like BF3, right, that is symmetrical, and even though all those bonds are highly polar toward the fluorines, if all 3 of them are polar, they'll cancel out, and that will be nonpolar. So we need to watch for that as well. Okay, let's get a couple more examples, and then probably one more video to talk about molecular orbitals, the kind of last issue in chapter 9. And the last one we'll talk about this semester. So we're getting there toward the end. So let's look at one that's got a little bit more going on in the central atom. Let's do selenium tetrachloride. So if we put selenium in the center, right, we could look and see that selenium is less electronegative than chlorine. Surround it with the chlorines to make the skeleton, right? That would be a good start. Selenium is in the same column as oxygen and sulfur, so selenium brings 6 valence electrons into bonding. Each chlorine brings 7, so 4 chlorines would add 28, and that would be 34 total electrons in this molecule. Now, we used 8 already because we made 4 bonds, so 34 minus 8 would be 26. So we'd start by filling in the chlorines, right? And each needs 6, so that would account for 24 of the 26 electrons we still need. But at that point, the remaining electrons will go on the central atom, so they would go in on the selenium. Right? Now, looking at the structure, 0 formal charge for all the chlorines, right? And we've satisfied the octet rule or more for every element here. 0 formal charge for the chlorine, 7 minus 1 minus 6. That's great. Selenium would be 6 minus 4 minus 2. Okay, that's also 0, so that's good. So that seems like a good structure. If we look at the structure, we would identify 5 sets of electrons. 1 is a non-bonding pair. That is a seesaw. So it would really look something like this. Chlorine there, chlorine there, chlorine there, chlorine there, right? And then the 5th spot, or what would be the 5th spot in the trigonal bipyramid, is occupied by the lone pair, right? Don't forget all your electrons around your chlorines, right? And around your central atom. Don't want to forget those either. But once we identify this geometry, this is not going to be a nonpolar molecule. Because of the lone pair here, as long as there's any polarity difference going on here, it cannot all cancel out. So that chlorine's pulling away from selenium, this chlorine's pulling away from selenium. Those two actually would cancel each other out. But both of these are pulling toward the right side of this structure. And since there's no bond on the left side to counteract that pull, this side of the molecule would be where electrons are pulled to and would be partially negative. The other side, opposite side, would be partially positive. This would be a polar molecule. So you end up with a seesaw-shaped molecule, it's going to be polar. You end up with a T-shaped molecule, it's going to be polar. Because one of those positions in the T will not be capable of being canceled out by the bond dipole of another part of the molecule. Okay? All right, so I think that hopefully is a little helpful in terms of going through the whole process to identify shape and then carry that on to polarity. Like I mentioned, there's one more topic in Chapter 9 I want to briefly discuss, which is molecular orbitals. So we'll do that in one more video for Chapter 9.